Welcome back to my course Formal Methods for System Verification. We will continue our discussion on ROBDD. In today's class, we will learn more about the variable ordering in ROBDD. So, as we have discussed in previous classes that the ROBDD is a canonical representation. So, it can give a very reduced size or representation or unique representation for given function, but the size of the generated VDD highly depend on the variable order, right. For the same function, if you take one variable order, that may give you a linear size ROBDD, but if you take another order, that may give you exponential size. But unfortunately, given any arbitrary function, identifying which is the best order is NP complete problem. So, we cannot decide always. But in today's class, what I will do, I will try to give you some tricks. In some scenario, you can actually decide the variable order that will give you the good VDD. But this is not a generic rule, but it's maybe applicable for certain functions. Okay? And the tricks is basically, if you have a control variable are closer to the root of the VDD. So, you try to put the more important variable closer to the root, and if there are related variable, they are also be closer in the ordering, right. These are the two kind of heuristic, I would say, which can help you in getting a good VDD. So, what I will do today, I will effectively take two examples, one for this and one for this, okay. And I will show that what do you mean by this control variables order or keeping them closer to the root, and what about the relative variable order. So, let us take this control variable case for this comparator. In previous class, I have talked about, I have shown you how to construct the ROBDD of 2-bit comparator. So, in general, if you think about that, I have two number which is 32-bit and I have created the comparator A greater than B, right. So, say A has 32 bits, A31 to A0, A31 is the MSB and this is the LSB, right, and B is again 32 bits number, B0 is the LSB and B31 is the MSB. So, I have to create a BDD of the 64 variables. Okay. You can see there are many orders. So, factorial, so there are 64 variables. So, there are factorial 64 possible orders are there, and some of the order is like that I put A1 bits first, then I put B0 bits. It may be in a reverse order, here MSB first, LSB last, or I put LSB first followed by the MSBs, right. And then I put B from MSB to LSB, or I can alternate them, right. So, I put A1 31, then B1 31, then A0 31, then B0 31, 30 and so on, right. So, this is basically keeping each bit closer, right. So, the MSB of this first, then the MSB of the B, then the second bit, second MSB bit of A, and then second bit of 3. This is some possibilities, but there are many other possibilities. Now, the question is that which order will give you a good VDD for this. Okay. So, here if you look into this comparator, what we effectively do to comparator, we will check whether this bit is 1 and this bit is 0. If this is the case, that this A31 and B31 dash, this is 1, this is 0. That means this the MSB of this bit is 1 and this is 0. So, I do not need to check the rest of the bits, right, because I have already decided that this MSB of A is 1 and this is 0, this A must be greater than this. So, I did not need to check anything, right. So, once they are same, right. So, if this is the case, I get the result. If they are same, how do I check that? I check by this generic formula, that if AI bi and AI dash bi dash, it means effectively A31 and B31 or A31 dash B31 dash. So, they are same. If they are same, then I will check the next bit, that A30 is 1, B32 is 0. So, this way it will continue, this is the equation, and finally, for the last bit, when all 31 bits are same, then only I will check the last bit, right. So, it means when I come here, it means all 31 MSBs are same, only the last bit I am comparing, right. So, this is the kind of function that will check A greater than B. Now, you see here what I am talking about, the control variables. So, what I am saying here is that if you know this A31 and B31, right. So, if I know that A31 is 1, B32 is 0, I do not need to check the rest of the thing, I can directly go to 0, right, or 1. If they are same, then only I will go to the next BDD. So, here A31, B31 are control variables, right. So, in a good order, I must keep A31, B31 is the first in the order, right, then A32, B32, A30, B30, then A29, B29, and finally at the end A0, B0, right. So, the good order is effectively this, and here because I am keeping the control variables higher in the order. So, A31, B31, A30, B0, so on, right. So, that will give you a good BDD, right. So, this I have already constructed in the last class. So, I am not going into detail. So, here the order is A1, then B1, then this is A0, then B0, right. So, this is how many nodes? 1, 2, 3, 4, 5, 5 nodes. Now, if I consider the different order, say A1, A0, then B1 and B0, right. If this I consider this order, this is the BDD I will obtain. So, I will highly suggest you to construct this using the direct construction using the same function, right. So, I have already talked about the function that I talked about here. You can use the same function to construct this BDD, you will end up getting this. Now, look closely, how many nodes are there? 1, 2, 3, 7 nodes, right. So, you basically have kind of exponential nodes, right. Here you have only 5 nodes, right. So, I will talk about this. So, now you see here what I am saying here, if I have A1 equal to 1 and B1 equal to 0, I do not need to check A0, B0, I can come directly to A1, right. Similarly, if A1 is 0, then if B1 is 0, then only this A0, B0 is coming. But if A0 is 1, B1 is 1, I can directly say that this is 0, right, A is not greater than B. So, this places where I am not putting any other nodes, that is why the size of the BDD is getting reduced, and this is the checking between A0, B0, right. So, internally if you have this order, control variable higher in the order, you have less size, right. Here you see here, if you take A1 and A0, I cannot conclude anything unless I see B1. So, only when I see B1, then only I can, if B1 is 0, I am already done, because this is A1 equal to 1, B1 equal to 0, this is 1. So, all these nodes are coming because I cannot have any decision can be made till level 1, because A0, A1 cannot decide about this. So, it is a bad order, right. So, that is why all these nodes are coming. Only when I have B1, then I can take some decision, right. So, even if you put say B0, A0 first, so here A1, A0, B1 and B0, right. So, if you put B0 above this, then it will be worse, right. You have more nodes, because you cannot take decision until you get to B1, right. So, in general, if you have this order, you effectively get order of n size BDD, but when you consider about the 32 bits, right. But when you consider this order where A1, A0, then B1, B0, you will have 2 to the power n number of BDDs in a BDD which have exponential number of nodes. And when you get the idea here, right, because you are effectively cannot take decision up to this level, sometime not this level, you have to go to the last level, right. So, then only this way the number of nodes will increase, okay. So, this is one thing. So, now the related variable ordering. So, here if you see here, this is the formula I am talking about. You again you have 6 variable, you can have 2 to the power 6 possibilities, which is the good order, right. So, one order can be x1, x2, x3, x4, x6. One order may be keeping these two together. One is basically say x1, x3, x5. So, what I did, I just put 1 x1, x3, x5 and then x2, x4, x6, or you can have say x1, x2, then x3. So, this is this order, right. So, I am keeping them together, right. I will show you that this order is good, because the relative variables, the related variable x1 and x2 is related, right. If I can identify that x1, x2, I do not need to check the rest of the formula, right. I can decide the formula is true itself, because x1, x2 both are say true. So, keeping this x1, x2 together, x3, x4 together, x5, x6 together is better in this scenario, because the related variable are closures, right. So, I will just quickly show you the BDD. So, suppose I have this construction, I will not show you the direct construction, I have example here. So, that direct construction method that I talked in the last class. So you start with, so if you have this formula, let us say this is my B1, right, and this is my B2, right. So this is my B1, this is my B2, right, and then I can actually apply, because it does not have x1. So this is the rule 3. So x1 will become the root, and then if I put here B1 x1 equal to 0, this becomes 0, right. So this becomes 0 or B2, and here if I put x1 equal to 1, this become x2. So this become x2 or B2, right. So again I have to construct the B2 is basically this entire formula. So now I have to take B2, and again I have to apply these rules here, x2 or B2, again I have to apply the rule, right. So this way I can continue, right. So for example here x1 equal to 0, I am now consider only this one, right. So here I have only B2 which has say this and this. So now I can consider this is B1 and this is B2, and then since x3 comes before x5, so x3 will be the root node, and I am going to construct this way, right. So I will just restrict them and will get it, and finally if I keep applying this I will get this BDD, right. So this BDD has 1, 2, 3, 4, 5, 6 nodes. So you can see here if x1 1, x2 1, I get 1. If x1 is 0, then only I am thinking about x3 x4, and now x3 is 1, x4 is 1, this is then. If x3 is 0, then only I am thinking x5 x6, right, x5 1 or x6 1, then I will get 1, right. So if it is x1 1 and x2 0, again I will come back to x3 x4 and so on. So this is the BDD I will get if you construct completely. So with this, how many nodes I get? 1, 2, 3, 4, 5, 6. Now I will show the BDD corresponding to say x1, x3, x5, then followed by x2, x4, x6. If you construct this, you will get this BDD. Again I am not showing the detail of the computation. How many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14 nodes. Earlier I have 6 nodes. So this is exploding. And why it is happening? Because you have the formula x1 and x2, then or x3 and x4, or x5 or x6, right. Now even if you take say x1, x3 and x5, right. So till this point you cannot make any decision, you have to create all nodes here, because all possible value of x3, x5 you have to consider, then only whenever you got x2, if this is 1 I get 1, right. If it is 0 I have to consider x4, if it is 0 then I have to consider x6, right. So this is how the BDD size is growing, because you cannot take any decision until you go lower in the order. So hence you have to keep all possible options open, right. So in this case I have shown you that it has 6 nodes and this has 14 nodes, right. So in general, I mean if you have a very big formula of say n variables, you can say that the size will be order of n, because there are 6 variables, 6 nodes. But if you consider this order, you will have exponential number of nodes, okay. So this again shows that how this keeping the variable which is related in the function keeping together or close to each other can reduce the variable size, okay. So there are a lot of research is there for different functions and all. So I am not going into detail of that, but just giving you an idea that how you can choose variable order in certain scenarios, which where you can actually reduce the BDD size, okay. So with this we conclude the discussion on BDD itself. Thank you.